Our chosen product was jet engine turbine blades. They're used in both commercial and military aircrafts. Commercial jets have combustion temperatures up to 2000 degrees Celsius, so with the original blade material used having a melting temperature of 1300 degrees Celsius, it is important that these alterations to the material are consistent and reliable. With over 150,000 commercial flights alone per day in the United States, it is important that these blades can perform reliably in order to get passengers to their destinations safely and efficiently.
Diffusion is important in the design and manufacture of jet turbine blades because we need to know what metal or alloy to use for the blades that would be able to withstand the high temperatures experienced from the jet engines. The alloy used for the turbines is a titanium, aluminum, and vanadium alloy. The alloy was probably used because it can withstand the high temperatures, and the process of diffusion made the alloy stronger so that they can withstand more forces during flight.
One of the key aspects to consider when optimizing properties for diffusion is temperature. At high temperatures, single crystal structures can slide against each other in a phenomenon called creeping, which causes impurities to diffuse along the grain boundaries of the typically steel and nickel alloys. The melting point of each element must also be considered, because if the temperature of the engine exceeds the melting point, malfunction would obviously occur. Additionally, higher temperatures means a greater rate of diffusion, so this must also be considered. Another important aspect of diffusion that needs to be understood is diffusion between alloys. Because of the variety of materials involved in the turbine and the variety of concentration of each alloy, it's important to consider how the atoms will interact with each other. By definition, diffusion is the movement of atoms from higher concentrations to lower concentrations. An example of how this is taken into account is a platinum pin being placed among steel alloys. These pins holding the core in place are purposely diffused into the steel without affecting any of the steel's properties. This deliberate use of diffusion is an excellent example of utilizing material properties advantageously.
Now let's look at parts that seem relevant to this example. Well, first of all, vacancy diffusion, which is a type of diffusion that happens with nickel superalloys. You want aluminum and nickel to combine in such a way that nickel goes at the center of the FCC face while aluminum at the corners. This is necessary and only possible through vacancy diffusion, where you expect either the nickel or the aluminum to go into the vacancies produced by the other metal. Grain boundary is also a driving force in single crystal blade production, since you want to avoid them, given the fact that they're more reactive than the grains themselves. Now, following with equations, while the solidification of the superalloy is taking place, the platinum pins inside the mold also diffuse into the molten superalloy. This means that it's necessary to know the diffusion coefficient, which then contributes to a fixed second law for us to understand the pertinent parameters, so that this diffusion happens well without imperfections. Also, here's an illustration of vacancy diffusion, where this space is expected to be filled by the diffused metal.
By default, all the chapters previously covered are going to be significant. However, the topics covered in Chapter 3 are the most relevant. Since jet engine turbine blades need to withstand tremendous force, they are often made of a single metallic crystal rather than multiple. Chapter 3 goes into detail explaining this concept, covering crystallography and crystal structures.
Chapter 5 is also relevant as it covers imperfections in solids. We've learned that the imperfections of materials is just as important as the materials themselves. In order for a high-strength, single crystal material to be manufactured, these imperfections and vacancies need to be fully understood. Chapter 2, which discussed atomic structure and interatomic bonding, is also fundamental for this turbine part. The structure and bonds that the metals make must be understood to make a part as precise as jet turbine blades.